hadrons. So I hope we have a bunch of nice talks scheduled today. So again, I'll turn it over to Clara now to convene.
Do you see my slides?
Yes, we can see them.
Okay, so let me begin. Good morning, everyone. I'm going to discuss the mass radius of the proton, basing on my recent paper. So the mass radius is clearly a fundamental property of the proton, which so far has not been determined. And we do want to know how the mass is distributed inside the proton. We want to know if it's associated with quarks or with gluons. And of course, we want to find a way to measure this mass distribution in experiment. So this motivates the talk, in which I will discuss gravitational form factors, scale invariance, and scale anomaly in QCD, the way in which we can measure the mass radius of the proton using quarkonium photoproduction near the threshold. We will present the extraction of the mass radius from experiment of GluX collaboration. And this will bring us to the mass radius puzzle. So the first point that I would like to make is that in non-relativistic weak gravitational field limit, the distributions of mass and the distribution of the trace of the energy momentum tensor coincide. So indeed, the distribution in space of T mu and T00 in weak gravitational field are identical. And in fact, the first version of theory of gravitation, which linked the energy momentum tensor to the properties of space-time, was the scalar gravity proposed by Nordstrom in 1912, which had this form and linked the trace of the energy momentum tensor to Ricci scalar. So this theory had a correct Newtonian limit. And the only thing which ruled it out was the fact that in this theory, light was not bended by a gravitational field. So once this was established, Einstein promoted this equation to the current tensor form. But for weak gravitational fields, there are no distinctions between scalar and tensor gravity. And this is why distributions of the trace of the energy momentum tensor and of the 0,0 component of the energy momentum tensor are identical. So this means that in this limit, if we can measure the distribution of T mu inside the proton, we will know the distribution of mass. So it's clear to see that these theories indeed give us correct Newtonian limit. And if we look at the form factor of the energy momentum tensor, then it has three different Lorentz structures. Of course, the energy momentum tensor is conserved, and this parameterization takes this into account for on-shell nucleons that satisfy Dirac equation. So in the limit of zero momentum transfer, only two structures contribute. And because in the rest frame of the nucleon, the matrix element of the Hamiltonian density should give us the mass, we get this normalization condition for G1 and G2 at zero momentum transfer. So their sum has to give us the mass of the proton. And likewise, we can look at the matrix element of the trace of the energy momentum tensor using the expressions that I showed before. This gives us the scalar gravitational form factor. So I call it scalar gravitational form factor because this would be the only form factor in Nordstrom's scalar gravitational theory. And again, at zero momentum transfer, we have the same normalization condition, which tells us that G of 0 is equal to M. And of course, it is consistent with our previous condition because this structure vanishes at Q equal to 0. And here we have G1 plus G2 at 0, which we already normalized to M. So everything is nice and consistent. So now the statement that the form factor of T00 and of T mu mu coincide in the language of form factors can be established if the following inequality holds. So G1 and G2 of 0 over 4m, where m is the mass of the nucleon, has to be much smaller than the slope of these form factors at small t. So now why do we get this difference between the two form factors? It's easy to understand the physical origin of this quantity because the form factor of T00 is frame dependent. And if we consider the gamma factor of the proton in bright frame, we can see that the proton is Lorentz contracted. And if you plug in for a typical momentum transfer, this compositeness scale of the form factor, you easily understand the reason why this difference arises. Nevertheless, for massive bodies, the compositeness scale must be much smaller than 2 times the mass of the object. In other words, the size of object must be much larger than its Compton wavelength, which is what we call weak gravitational field limit. And in this limit, which as we will see holds for the proton to reasonable accuracy, the form factors of T00 and T indeed coincide. So then we can use the form factor of the energy momentum tensor to define the mass radius of the proton in analogy to the definition of the charge radius from the electromagnetic form factor. Moreover, in relativistic region, it is natural to consider the scalar gravitational form factor since the trace of the energy momentum tensor is the Lorentz scalar. So the trace of the energy momentum tensor also plays a special role in field theory. It is a generator of dilatations. And the theory of dilatations was developed by Hermann Weyl and others. So you can see that dilatations correspond to dilatational current. And if you compute the divergence of this dilatational current, as you can immediately see from this formula, the divergence of dilatational current is equal to the trace of the energy momentum tensor. So it really measures the violation of scale invariance. So for example, if you take Maxwell electrodynamics without sources at classical level, then the trace of the energy momentum tensor vanishes. And this is precisely the reason why in scalar gravity, there was no light bending by massive bodies. So in QCD, if you compute trace using just classical field theory, this is what you find. And there are two problems with this expression. First, a potentially large contribution from heavy quarks to the masses of light hadrons. If you take a matrix element over light hadron states, then this term potentially can contribute a lot. And even if you decide to forget about heavy quarks and just leave this piece out, then another problem that you run into that in the chiral limit of massless quarks, all hadron masses would vanish. So we know that this problem is solved by trace anomaly of QCD. There is a quantum contribution to the trace, and the loops that contribute here are the same loops that drive the asymptotic freedom. And that's why the coefficient of this operator involves the beta function. So this expression solves both of the problems that I pointed out, because the heavy quark piece of the trace cancels at small momentum transfer against the heavy quark piece of the beta function. So only light quarks appear in the final expression. And moreover, now the masses of light quarks do not vanish in the chiral limit of massless quarks, in which limit the entire mass of the proton originates from the gluons. So now, how do we measure the distributions of the trace of the energy momentum tensor? So one way to do it is to utilize heavy quark anti-quark states. So the theory of interaction of heavy quark anti-quark states with gauge fields is completely analogous to the theory of interactions of atoms with electromagnetic fields. So one of the pioneers was Mikhail Voloshin, who tragically passed away last year. And the leading operator here is the quadratic chromoelectric field operator, which can be decomposed into the trace of the energy momentum tensor. B is the coefficient of beta function, and G squared times T00G. So now, after we take the matrix element of this over the proton, then this is normalized to the proton mass at zero momentum transfer. And this term appears subleading because it is suppressed by the small coupling, which is not present here after you perform this matrix element, after you take the matrix element. So this means that we can use photoproduction near the threshold to extract the matrix element of G squared, E squared operator, and thus in the leading in G squared order, the matrix element of the trace of the energy momentum tensor.
You have now 2 minutes to go.
Yes, so now close to the threshold, we have substantial momentum transfer in this photoproduction process. And this means that if you want to limit ourselves to a small velocity of G psi, the center of mass energy in this process has to be small. So then we write the amplitude using standard formulas. We write the differential cross-section. And then we now have the data from GluX collaboration exactly in the desired energy region. And this data can be used to extract the parameter of the trace of the energy momentum tensor form factor using the dipole fit, and extract the corresponding mass radius of the proton, which appears to be 0.55 plus minus 0.03 Fermis. So this is much smaller than the proton charge radius, which is, I think, very interesting. And of course, there are some theoretical uncertainties, but I think they do not account for the difference between the two extracted mass radii. And the reason behind the smallness, relative smallness of the mass radius, in my opinion, is the decoupling of Goldstone bosons from the trace of the energy momentum tensor, which makes the mass radius significantly smaller. So we will soon have a lot more information about this from GlueX, from SOLID, eventually at EIC, and probably also from ultra peripheral collisions at RIC. So there is a lot to look forward to. And I will leave you with this summary saying that we have an evidence for the smallness of the mass radius of the proton from experimental data. And of course, we have to understand the origin of it. So thank you very much.
Thank you very much for the talk. We have time for some questions now, so if you can please raise your hand. There is one question from Surek. Please, if you can read it.
Thank you. My question is, but we know that this, from the data, from T dependence, we have energy dependence. So how you extract, for which energy you extract this radius? Because I thought for different energy it is different, or
yes. So in order to extract this radius, you have to ensure that this scalar operator without covariant derivatives dominates. So operators with covariant derivatives bring in the factors of velocity of J psi squared in the center of mass frame. And because I want to suppress these operators with derivatives, so I have to limit myself to the kinematical region in which the velocity of J psi is less than, let's say, 0.2. So then corrections are velocity squared. So this limits contributions of operators with derivatives to about 5%. So this tells me that the energy of the photon has to be below 9 or 10 GeV.
So this is really a region of JLab.
This is really a region of JLab. So this is where this region is. We used to have some pretty low statistics data from Cornell. Slack data did not extend to this region. And now you can see that GlueX now for the first time has data in this region. So I don't believe that data on T dependence at higher energies can be used to extract the mass radius.
Thank you.
Okay, thank you very much. Next question from Nodoka Yamanaka.
Hello. Is it possible to also measure the pressure distribution and the shear viscosity with the same framework?
Well, I actually am a little bit doubtful about application of things like, shear viscosity to the proton, because shear viscosity is a measure of dissipation, and a proton is a pure quantum state. So I don't think shear viscosity is, I have my doubts whether it's a meaningful quantity. So for the pressure, I think it should be possible to do it, but you would have to look at matrix elements of TII, and this is different from the problem that I considered. So probably virtual Compton scattering would be a better process to do this.
Okay, thank you.
Very last, very quick question from Marat Sivikov.
Can you hear me?
Yes, I can.
Dmitri, I have a question about your theoretical basis of evolution. As I can see, your analysis essentially relies on two gluon dominance interaction between proton and heavy quarks. I wonder if multi-gluon contributions will significantly affect your analysis. I mean multi-gluon exchanges between heavy quarks and protons.
Yes.
And I'm a bit concerned because now we know about bound states as the so-called pentaquarks, which exactly should appear in the near threshold kinematics, which you consider.
Yes. Okay. So, so indeed, of course, one has to worry about high-dimensional operators. So in operator product expansion, they come with powers of 1 over heavy quark mass. So they should be suppressed, but you know the coefficient of 1 over m, of course, can be large. So one way in which we can test the contribution of these high-dimensional operators is to perform this measurement with upsilon production at EIC. So if the high-dimensional operators are indeed suppressed, as I expect them to be, then the mass radius extracted from upsilon measurements would be the same. And regarding the size of this object, please keep in mind that we are here very close to the threshold. So the characteristic distance between heavy quarks is really 1 over MC and not 1 over J psi radius, as it would be in the on-shell interaction of J psi with the proton. So I believe that the conditions for the applicability of multiple expansion here are much better than for the interaction of on-shell J psi with the proton.
Thank you very much. Thank you very much for this nice talk. Next, we have Dr. Qian Yang. You can share your slides. From Shandong University, he will talk about J psi production in jets in PP collisions at 500 GeV by star.
Okay, can you hear me?
Yes, we can.
Can you see my slides?
Yes, that.
Okay, so, okay. I'm Qian Yang from Shandong University. So it's my first time to have attended this conference. So today I will talk about the J psi production in jets in PP collisions at 500 from star experiment. So basically I will talk about why we want to start the J psi and what's the star experiment is, and then our measurement, and give you a summary. So let's come to the first part. So why we want to start the J psi productions. First of all, J psi is a multi-scale systems that enable us to probe the both predictive and non-predictive range. By looking at the J psi production process, you can see that when you produce CC by pairs, it normally has a large momentum transform. So this process is a predictive process. However, for the evolution of the CC bar into a J psi, normally have the small dynamic scales. So that's a non-predictable process. That's one reason. And for on the other hand side, when you look at the J psi itself, it's due to the large mass of Chuang quark. So the J psi is a non-relative QCD systems. It's also so it makes the J psi as one of the simplest QCD systems. So of course we have some other Quarkonium systems like the Pusat2s and Upsilons. But in experimentally, it's easy to measure the J psi because it has a large decay boundary ratio to the leptons and a large production cross-sections compared to protoniums. So this makes the J psi an ideal test ground of the QCD. So talking about the models, so because chipset production involved a non-particularly precise, so we can only try to understand it through the models. The different models treat the cisbar production differently, and also the hydrogenization process differently. Let's see, look at the countersinglet models. It assumes the cisbar produced in a countersinglet states, and then it evolved into a gypside. For another models like NRQCD approach, it assumes that the cisbar can be produced in a singlet states, but also the counter-octet states. Then the counter-octet states evolve to fantasy gypside by reading out some soft gluons. So for these models, NRQC approach, so they use a non-distance matrix element to describe it in the soft precise. That's also other model like the improved color evaporation models. It assumes the cisbar pair has certain ability, possibility to evolve to a gypside. Then look at the measurements we have expression at the rigs. So normally we have two very important observers. One is the gypside cross-sections, another one is actually polarization. Let's look at our measurements at 500 GeV PP collisions. This is the gypside spectrums as function of PT. You can see actually this is the PT range we have at the rig energy from 0 to 20 GeV. And you can see actually we compare to different models like the NRQC approach as a high PT and the no PT parts. And you can also see this compared to the color evaporation models with the follow which includes the B2 gypside decay contributions. You can see also consistent with our measurements. That's the cross-section side. When you look at the polarizations, you can see actually different polarization, the polarization measurement results. It's compared to different models. You can see all consist with our measurement. So currently we have very limited discrimination power to different models. So how do we further understand it, whether we have more stickiness or we want to develop a new or develop a new observers? So gypside in jets has been proposed as a new observers. So when a high energy parton fragmentation into a gypside, so null plots here show you the momentum fractions carried by gypside as a function of this normalized basically fragmentation functions. When you look at for the gluons and charm quarks, the fragmentation functions to a gypside is totally different. And on the other hand side, when you look at the non-distance matrix elements, which is described in the cisbar evolved to a gypside, different groups have different values. So when you look at use this non-distance matrix parameters to describe this fragmentation function, you can see at a different jet energy. So you can see here, the fragmentation functions are very different. This basically tells us the different fragmentation patterns for different production mechanisms. So at STAR, actually this has STAR can measure the gypside through the E+, E- also the dimuon channels. But in this talk, I only talk about the di-interaction channels. We use time projection chambers, actually, which used for the trackings, which can measure the charge particles momentum and also measure the particles dEdx energy loss in the TPC, so we can do particle identifications. And on the other hand, we can do a better electromagnetic parameters. This is used for the trigger and also the identification of high PT electrons. And then let's look at the gypside constructions. So basically in the jet reconstruction, we use the NTKT, but only use the charged particles plus chip-side candidates. We also need to exclude this electron and positron, which come from the chip side. So left plots show you the invariant mass distributions for the Nixon pair, and also you have some random combinations. We use the Nixon pair method to estimate it. After we subtract this combinatorial background, you can see these red dots still have some residual background. This is mainly from the Joyan, CC bar, and the BB bar contributions. So we use experimental function to describe it. And for the chip size signal, we use CRISPR functions. Then come to the chip size inject. So the x-axis is the transverse moment fractions created by chip size within a jet. And the y-axis is basically the normalized, it's a self-normalized, the self-normalized values. The normalization reach is from the 0.6 to 1. You can see a value that's larger than 1. That's because this point is exactly equal to 1. We remove two here for visibilities. So this is the first measurement of chip size production in jets at rake. So all the detector effects has been corrected by using unfolding methods. So you can see the data itself, we don't see significant Z dependence within current uncertainties. So that's one thing that we can look at, nothing whether this has any cone size dependence. So by default, we use I equal to 0.4. So we narrow down to 0.2 and 0.6. So you can see for this being, actually you do see some difference, but this is mainly due to you have a certain acceptance, detect acceptance. When you do a normalization, this difference disappears. For the other data point, the current uncertainty is still not. So we need more data to start the R dependence. A very nice data sample is coming. The analysis is ongoing. So this may give more hints on the this R dependence. So then next thing we can look at is actually what is compared to the PCR. A PCR is actually based describe the chip size production based on the leading order inaccuracy approach. So when you look at the PCR, you see the gray band, gray field histogram here. Actually, you can see actually we have a very different trend compared to our measurements. Chip size production is less isolated in data than in PCR. And by looking at the different trend, actually, this will help to understand the chip size polarizations. And also for the production, actually, whether it's from shower, pattern shower, or the pattern scatterings. So another very interesting things actually also compared to the measurement at the rig and compared to what at LHC, we have the collision energy has an order of difference. So also we have very different jet measurement method. At start we used the charged jets, but at the LCB and CMS, what they use is actually full jets. So in both cases, you can see they also compare those leading order inaccuracy is also the PCR, and the CMS is also the PCR. You can see, but the jet PT range is totally different. As you can see, this 25 to 35. What we have is not than 10. And also for the LCP, it's also not than 20s. So despite all the difference, you can see they have a very similar, less isolated production scenario pictures. So all this is very interesting. This tells us some underlying production mechanism and behind both at rig and LHC. So another interesting, so that's we first look at the shape. Then we may ask how many chip sizes are produced within a jet. That will give some additional information about the chip size production precise. So here we do the same thing, but we normalize by the number of gypsy, not by required PT less than 5 GB, the inclusive gypsy. So you can see this data, it's systematic above the PCF8 results. This tells that in the real data, more gypsy produced within a jet compared to the theoretical calculations. So and the fractions we have is around 3.7. With for a gypsy produced within a 10 GeV jets here. So then let's go to my summaries. This is the first measurement of gypsy production in jets at Rick energy. And currently we didn't see significant Z dependence of jet to gypsy fragmentation functions. For jet PT less than 10 GeV and also required gypsy PT less than 5 GeV. Compared to PCF8, which is the leading order NRQCD, so we see a less isolated productions in data, and more gypsy are produced within a jet in data. And also the similar observed of less isolated gypsy production in jets compared to PCI at both RIC and HC, despite all the different jet measurement method and also different kinematics range. And also for the jet cone size dependence, we need more data to do so. So the final thing that I want to say, actually, we are very welcome for the theoretical inputs to make a comparison of our data to theoretical calculations so that we can learn more about this. I think that's all. Thank you. Hello. Hello. Hello.
I can hear you well.
Okay. Yeah.
Okay, I have a question. I don't know.
Anyone talking?
Convener is not speaking.
I think you're muted.
Clara, you're muted.
I'm very sorry. I'm very sorry. Jean-Philippe, I was waiting for you. I'm very sorry.
Okay, sorry. So I have a comment and a question. So as you said at the end, theory inputs are very welcome. And in fact, this pointing back that like most of us, I guess you consider the PTR8 are not quite theory. In fact, PTR8 is probably leading order based picture, and it clearly doesn't work out. So we should make clear that PTR8 is not complete theory here. But my question is, it was advocated in the people who introduced this idea of observing gypsy in jet, that in fact what should be measured is that is when you fix Z, the gypsy fraction momentum, and then you increase the energy of the jet, you should see how this evolves. And this is how you should discriminate between the model. What you do is like LHCb, you only look at the Z dependence. So do you have some plan to fix Z and then to change the PT of the jet?
Mm-hmm. I agree. I also noticed the mismatchment. So basically, currently, this is our first measurement result. So the next step, the matches is energy dependence at a fixed Z. It's our next schedule to do so. But you also know this may need a lot of statistics to do so. We have two huge data samples. One is from 2017, another one is actually well scheduled to take a very large data sample on next year. So this will help us to further get these measurements. Yeah.
Okay, good. Thanks.
Very well. Thank you very much, Qian Yang, once again for your talk.
Mm-hmm.
Then we can move to the next speaker, who's Carlo Flore from IJC Lab or SEM. He'll talk about next to leading order inclusive J-psi photo production at large PT in HERA.
Hello.
Hello?
Can you hear me?
Yes, we can.
Okay. Try to share my screen. Do you see my screen?
Yes, perfect.
All right. So first of all, thanks to the organizers for allowing me to present my work here. I will talk about NLO inclusive J-psi photo production at large PT at HERA and the EAC. This work has been done in collaboration with Jean-Philippe Landsberg, Guangsheng Xiao, and Lisa Yedelki, and is published in Physics Letters B. So to start with, let me remind you a few things about the Quarkonium production model. As said in the previous talk and also by Charlotte yesterday, there's still no agreement on which mechanism is dominant. There are indeed different mechanisms that take into account different treatments of the hadronization. There are three common models. The first one is the core singlet model, in which the hadronization happens without gluon emission. And so the CC bar pair, the QQ bar heavy quark pair, as the right quantum number to produce the quarkonium in the final state. Then there's the non-relativistic QCD that embeds core singlet model and core octet mechanism. So in an RQCD, we take into account also higher Fock states of the mesons, and the QQ bar pair can be produced also in octet states with different quantum number as the meson. And finally, the core evaporation model, or its recently improved versions, that is based on quark hadron duality, and essentially here only the invariant mass matters, and semis of gluon emissions are taken into account, and the CC bar production and hadronization are core-wise decorrelated. In our work to calculate NLO cross sections, we actually use a leading PT approximation of NLO J-psi plus gluon called NLO star. NLO star contains essentially only the real emission contribution with a democratic infrared cutoff, Sij mean, or its square root. And this is expected to account for the leading PT contribution up to the NLO, so the ones that goes like PT to the -6. It has been already successfully checked against full NLO computation for PT larger than 3, and you can find this in these references. And for this reason, we try to compare our NLO star calculation with a full next to linear order QCD next to linear order calculation taken from this reference. Here we validate our calculation comparing our NLO star curves to a full NLO calculation for HERA kinematics. This is the kinematics adopting this value for LDME, transverse mass as factorization renormalization scale, this value for the Charm mass. And we see essentially that when we vary the red band corresponds to our NLO star prediction. When we vary this infrared cutoff in the interval 1 to 3 in units of Charm mass, this will approximate the full NLO calculation in black. And especially if we take the value twice the Charm mass, we remarkably reproduce the next to linear order result. In view of this, we want to revisit HERA data. The data that we revisit is this one published in 2010 with this same kinematic. And in the following, and we also show the data with a B2 J-psi fit down subtracted that was overlooked in the past. In what we will show that is all the computation are done with the Laconia, the code developed by Washeng, and I also invite you to look at our project called NLO Access. But anyway, what we will show, we will adopt this value for the core singlet J-psi LDME. We include a 20% of fit down of psi prime to J-psi. Again, we adopt transverse mass as factorization and renormalization scale, 1.5 GeV for the Charm mass and the CT14 NLO PDF set. So to pin down the different contributions that we consider, Let's start with the first contribution, the leading order QCD contribution at order alpha alpha s. And here you can already see two different bands. The hash bands are the scale uncertainties, and the solid bands are relative to the mass uncertainty on the charm mass. The second contribution is a new contribution that we take into account, that is the leading order QED contribution at order alpha cube. Then we have this other new contribution that combines the gamma charm to psi charm and gamma gluon to psi CC bar at two different orders and two different mass scheme, 4-favor scheme for the former and 3-favor scheme for the latter, that are combined in the leading order variable favor number scheme. And it's also a new contribution. And then we have our the sum of leading order and this two contribution at order alpha alpha s cube, that is the NLO star QCD contribution, and we have the overall sum that we indicate in orange here. And essentially, what we can say about this: first, we can clearly say that leading order QCD is already working well at low PT. The leading order QED is much smaller, as you can see here, but the spectrum is also much harder. Again, the JPSI plus charm channel starts to matter at large PT, and essentially the NLO star is very close to the data, and the overall sum nearly agrees with the data, especially when we include this B to JPSI feed down that is subtracted. So in view of this, we can say that at large PT, the core singlet model up to this order reproduces JPSI photoproduction data at HERA, and we will restrict to core singlet model for our EAC predictions. Let's start from the smallest energy configuration for the EAC at 45 GeV. The core code for the cures are the same. Here we have the kinematical range, the kinematical variables that we have chosen, and the other parameters are the same. At this energy, we enter into the valence region. So we see that the yield is steeply falling with PT and can be measured up to PT 1011 GeV with the largest luminosity reachable at the future EAC using both dielectron and dimuon decay channels and an efficiency of JPSI detection of about 80%. The QED contribution here matters. It is indeed the leading at the largest reachable PT. And in general, the gamma plus quark fusion contributes for more than 30% to the cross-section for PT larger than 8 GeV, especially if you look here at the breakdown of the different contributions. If we now move to the largest reachable energy at the EAC, the PT range, it's 140 GeV. The PT range goes up to around 18 GeV, sorry. Again, the QED contribution is leading at the largest reachable PT, but here the gamma gluon fusion is dominant up to PT around 15 GeV. We also see here that the production of JPSI plus 2R partons, either two gluons, a quark and a gluon, or a CC bar, is dominant in the region between 8 and 15 GeV. And this could lead essentially to the observation of a JPSI in the final state of a JPSI plus two jets, and these two jets will have a moderate PT. And this in a specific topology where the leading jet recoils on the JPSI plus jet 2 pair, and we expect that the cross-section will vanish when the energy of the second jet in the JPSI rest frame goes to 0. Next, we move to the JPSI plus charm associated production at the EAC. This is essentially what we show is the same leading order variable favor number scheme computation that we have shown in green in the previous plots, but here we take into account the charm detection efficiency. And we combine the 3-favor scheme and the 4-favor scheme in this way, with a counter term that will compensate will avoid double counting in the combination of these two schemes. At the smallest energy, at the AC at 45 GeV, the yield is limited to low PT, even when we consider the largest luminosity. But it's in any case observable if this charm detection efficiency is this, with these figures for the events at different luminosities. When we go to largest energy, the PT range goes up to 10 GeV roughly, with thousands of events with the largest luminosity, and this could lead to the observation of a charm jet. Let me underline that in the 4-favor scheme, so the channel gamma charm that goes to jet side charm depends, of course, on the charm PDF, and this could be enhanced by intrinsic charm PDFs. And so we used the intrinsic charm PDFs encoded in the 1314 next to next leading order PDF set, and we see that for both the C-like parameterization and the valence-like BHPS-like parameterization at the largest energy configuration at the AC, we don't see a clear signal. But if we go back to the smallest energy configuration, and again, we look at the C-like parameterization for the intrinsic charm, we can start to see something, but still it's not very visible. But if we look at the valence-like parameterization, so the BHPS parameterization, this peak would be visible. And so again, ESC would be can be an unavailable tool to also pin down intrinsic charm in the proton. So to conclude, again, we started saying that there's no agreement on Quarkonium inclusive production mechanism. For Quarkonium production, we know that QCD correction with PT enhanced topologies are known to be important, and in view of this, we have revisited JEPSI photoproduction at HERA. We have shown also that at large PT, the core singlet model can describe the latest HERA data for JEPSI photoproduction, especially when we include this new contribution like the JEPSI plus charm, and we take into account the B2 JEPSI feed down that was overlooked so far. So what we have presented is the first QCD correction study to inclusive JEPSI photoproduction at the EAC. And for lepto production, I invite you to look at the reference of Jianwei Chu, or also look at the talk of Sanjam Rajesh in the spin physics working group today. We have seen at the largest energy at the EAC that the QED contribution, that is a new contribution that we have included, is leading at large PT, that the gamma gluon fusion is mostly dominant, and the JEPSI plus charm jet is accessible, and also the JEPSI plus 2 jets is accessible. And finally, at the smallest energy configuration, again, the QED contribution is leading at IPT, and it's and in this configuration we will be also sensitive to the charm PDFs. Thank you very much for your attention.
Okay, thank you very much, Carlo. Very nice talk. We have already some questions from Nodoka Yamanaka.
Hi, Carlo. Thanks for the interesting talk. Do you have an idea of why for the photo production it's working well, while for the PP collision it is not working in the CSM? You cannot describe the JEPSI production spectrum, right? The PT distribution of the.
Well, I mean, these are two different processes. First, second, it is also true that if you look at the different fits for LDMEs, there are different descriptions of PP and NDP data, right? I think that probably the effort that we have to do is first to understand what is the bulk of the cross sections, especially when we do predictions for the future experiments like the AC, And then based on this, we can try to assess whether we have also opted contributions or not. Here, especially here, there were some aspects, for example, the B feed down that was overlooked for 10 years, I'd say. So I don't have a strong opinion on this, but I mean, phenomenologically, I think that this is the best way to proceed, to try to pin down what is the production mechanism.
Okay, thank you.
Thanks.
If there are not any more questions, there's one more question from Anastasia.
Hi, thank you very much. Very nice talk. I just have a very naive question. So you have all these contributions, and some of them are what you refer to leading and next to leading order and next to leading order star. What is the rationale for using the same order, well, the NLO CTEC in all of them? Like how do you match the order of the PDF with the order of your calculation? That's my question.
I mean, to my knowledge, I've seen that many examples of usage of NLO PDFs, even for leading order calculation. But I think that they don't differ very much in. I mean, the difference was not that large for leading order and next to leading order PDFs, as I recall from tests that we have done.
Okay, I mean, there would be some difference between, particularly between leading order and next to leading order PDFs, right?
Yeah.
So, yeah, I mean, I understand it's a complicated process, but in a sense, you know, I'm asking, you know, what would be the consistent way of doing things?
I mean, to be honest, I don't know. It's a question that I would ask too, in the sense that would you prefer to when you go to leading order to next to leading order, would you prefer to calculate the leading order with a PDF set and the next to leading order contributions with another PDF set and sum them together, or use the same PDF for both? I don't know what's the best thing. I think to be consistent, probably you use the PDF set that you use for the highest order. This is what we have done.
Okay, thank you.
Thanks.
Thank you very much, Carlo, once again. And then we move on to our next speaker, who is Vato Kartvelishvili. We will talk on behalf of ATLAS about ATLAS results on Charmonium production.
Hello, can you hear me?
Yes, we can hear you.
Okay, so let me try and share my slides.
Perfect, we can see the slides now.
Okay, unfortunately, I don't see what you see, but I can see my own slide. That's okay. Maybe once you stop your video, maybe I can see my slides. I don't know.
Okay.
No. Oops. That's a bit unfortunate. I don't know what I'm pointing at. You will not see. Oh, maybe you will see. Okay. Okay, so I'll be talking about ATLAS results on Charmonium production. This is obviously an important object of study. First of all, of QCD at the boundary of large and small scales. Study of production mechanisms has helped and will help, I would imagine, develop QCD methods. Various contributing sources to the JSI production can be separated experimentally, which makes it even more interesting and useful. And recently, Charmonium production is used more and more as a tool for various further studies, such as quark-gluon plasma studies and separation of single and double parton scattering using Charmonium as one of the particles. And also, even more recently, it's been suggested transverse momentum-dependent parton PDF studies using J size as one of the objects there. So let me give a quick overview of contributing processes. A large fraction of Charmonium states are produced in the case of B hadrons. Due to longish lifetime of the parents, these have measurable decay length between the production vertex and the decay vertex. And this length can be used to separate promptly and non-promptly produced J size, as you can see here on the plot for the variable which ATLAS calls pseudo-proper lifetime. The peak here around 0 tau is the promptly produced J size and Sci2Ss, and this quasi-exponential tail shows the contribution of non-prompt, which are coming from B decays. This method obviously exploits the property of the decay of Bs into J psi x, such that J psi tends to carry an almost fixed fraction of parents' momentum. So one of the parameters extracted from those measurements is the so-called non-prompt fraction of J psi. This seems to have quite a strong PT dependence, varying from about 0.1 at lowest PT values to something like 70% at the highest PT values. But there is no strong dependence on energy. The plots shown here, they cover some of these measurements are made at CDF and others LHCb at 13 TeV, and in the same range, the same shape is being observed. What I show on the left is a two-dimensional plot obtained by ATLAS a few years back at 7 TeV. Where you can see exactly that. So we start at around 8 GeV in PT, and there is a smooth rise all the way to about 70% at highest accessible PTs. Here are some results from previous studies with prompt J psi in run 1. Also shown are the ATLAS data and also CMS data, which cover adjacent regions of PTs and rapidities in the case of LHCb here. And you can see that there is a very decent description of the decent consistency and synergy between ATLAS, CMS, and LHCb in rapidity and PT. And also decent explanation, this decent coincidence with the theory predictions of NRQCD model. Let me stress here that all previous studies in ATLAS used dimuon triggers with 4 GeV threshold on each muon PT, which limited the range from the left, from the low PT side by about 8. But also at high PT side, because of muon-muon correlations at trigger level, the statistics ran out very fast after about 100 GeV in those measurements at 7 and 8 TeV. So a few general remarks about Sci2S production, which is usually also obtained together with J psi. Here is the difference in yields. You can see the difference is quite dramatic. So statistical errors in Sci2S are significantly larger. This plot here, the 2D plot, shows the ratio of Sci2S to J psi, which happens to be quite close to constant at about 4%, maybe rising to more like 6%-ish at the high end of PTs. But The range of Psi2S PTs is even more limited because of shortage of statistics at high PTs. A few words about an oldish measurement of differential spectra of C-even Charmonium states in ATLAS. This is the only absolute measurement at LHC between the LHC collaborations, while others have measured the ratios. ATLAS has measured the actual differential spectra of KIC1 and KIC2, both in prompt and non-prompt contributions, which happen to be in a good coincidence once again with predictions of NLO and RQCD model. So finally, getting to the main point, which is Charmonium production in run 2, energy is higher, and inevitably there is a sharp increase in muon trigger thresholds or a dramatic prescale, which makes them unusable. So the preliminary results I'm going to show here, these are obtained only in the region of high transverse momenta using a single muon trigger with a single muon transverse momentum threshold at 50 GeV. This was a trigger which was unprescaled for the full integrated luminosity of run 2, so we are covering 139 inverse femtobarn. So statistics is as high as it will be in run 2. This is all there is. So like I said, it provides coverage of high PT spectra, high PT range from 60 to 360 GeV. Any previous measurement, the highest value obtained for HSI was about 150, so that's quite a dramatic increase. For Psi2S, the range is limited to 140. After that, it's difficult to make anything up because of large statistical error. Rapidity range is covered in 3 bins. Here are some sample fits in individual PT bins. You see that the fit quality is good. You see that the resolution is getting worse at high PTs. Obviously, this is a tracking measurement. And a Psi2S peak is zoomed in those inlets. And at the bottom, there is the lifetime distribution. And again, you can see here that the lifetime resolution gets dramatically narrow because if you remember, there is a PT sitting in the denominator in the definition, and that makes that shrink quite dramatically. So what is measured are the cross sections of JSI, Psi2S, their ratio, and the non-prompt fractions of each of them. And most important systematics have been assessed. Here is a glance on the errors. So one can say that at low PT range, relatively low PT between 60 and about 140, is dominated by systematic measurement. For JSI, above that, it's all pretty much statistical errors. For Psi2S, it's statistical errors pretty much most of the time at around 10% every time. Here are the results in 3 rapidity bins from 60 to 360. So prompt on the left, non-prompt on the right. You may, if you are eagle-eyed, you may see a slight variation in shape, but then in the ratio, we will find out that the non-prompt fraction is actually quite constant in this range. Let me show those things. So once again, on the left, there is a plot of low energy measurement. And on the right is our latest measurement, which starts at 60. And you can see how the non-prompt fraction for JSI just continues and becomes quite flat. We still have to see whether this slight deviation from flatness at very high rapidity, okay, for ATLAS, high rapidity range, whether this is a real effect or could be some kind of systematic effect, which we'll try to assess here, but it's still preliminary. For Psi2S, there is not enough range to distinguish any behavior. It actually fixed at around 0.7, as we can see. This is prompt and non-prompt ratios separately. So this shows prompt production ratios between Psi2S and J-Psi. And it's also basically constant, and it's relatively on a high side. Naive estimate of branching times gamma should come up somewhere at 5.6, but there should be some powers of mass also coming in here. So it's interesting to see what the models have to say about this. We don't have any model predictions on these in this measurement taken into account. On non-prompt side, we do have FONLL prediction, and you can see it's right on the data points. So FONLL manages to describe the whole range of data quite well. For Psi2S in the full range. For J-Psi at high PTs, there seems to be a slight deviation. So data goes slightly higher. Sorry, FONLL goes slightly higher. We're talking about factor of 2 over 5 orders of magnitude. And by the way, I must say that FONLL authors never claimed that there is, they can predict all the way this far. Now, a quick word about the prompt distribution. Here for J-Psi, here we do not have any comparison with theory, but we have comparison with CMS data in blue points here, and the black points are these ATLAS measurement. So here we cover from 20 to 360. And there are seven orders of magnitude fitted to a very simple parameterization with essentially a power law coming up as n equals 6, which is quite interesting from my point of view. And I'd love to see some serious predictions from NRQCD-based model calculations compared to this data plot. Last minute, which I probably don't have, I would like to attract your attention to a number of associated production measurements of J-Psi with various other objects, such as a W, a Z, or another J-Psi, or W again at 8 TeV. Some plots are shown here for prompt J-Psi production at 7 TeV with the J-Psi, at 8 TeV with Z, and at 8 TeV with W. And one common feature here is that there is quite a significant excess over NRQCD predictions, especially at higher PT, even with smaller than usual sigma effectives, hopefully taking into account the DPS contributions, which is shown here with confusingly different markings on different plots. Okay, so I'm leaving you with a picture of Z plus J-Psi event. This is the J-Psi, that's these two muons are Z. And thank you for your attention.
Thank you very much for your nice talk. There are questions for Vato. There's one question from Jean-Philippe.
Hi, Vato. So that's super impressive to see this super high PT data. Can you go back to the result of the PT dependence of the prompt fraction?
Yeah. This one?
I'm not sure I see the right one, but maybe my connection is...
Is page 15 with the comparison with CMS and the
fraction. Fraction.
Oh, fraction, non-prompt free, that one, yeah,
this one. So I understand from this that the PT spectrum, I mean the production or the PT dependence of the prompt and the J-Psi from B is the same essentially. From
essentially, yes, that's what we see, yes.
That's a super strong result. So, and it seems you have the same also for psi prime.
Psi prime, we don't reach as high PTs as with JSI, but it's also here you can see that it is within between 0.6 and 0.75, pretty much all points are in that range.
That's amazing. I'm also looking forward for theory. So probably we can run with Nodoka, we can run the color evaporation model at NLO up to this IPT.
Please let me know when you do this, because I'm really, really curious. The slope is so close to 6 power of PT, 6 PT over 1 over PT to the 6th power, that it cannot be very complicated. I mean, underlying physics should be simple with a simple power law like that, right? Okay. Which it is not, of course, but.
Okay, thanks.
Thank you very much, Vato. Now we move on to our next speaker, who is Pieter Taels from École Polytechnique, and he will be talking about quarkonium production and gluon TMDs at the EIC. Yes.
Hello. I will try to share my screen, but first Vato should put down his screen sharing, I think. Thank you. Okay. And share screen. Does this work?
Yes.
Okay. Can you see the slides moving and all?
Yes, perfect.
Oh, very good. Then I shall start. So thanks a lot, of course, to the organizers and to the conveners for giving me the opportunity to give this talk. As you can guess from the title, I will talk about quarkonium production at the EIC. And specifically, I will try to study, I will explain some work together with my collaborators, in which we try to study whether inclusive quarkonium production at the EIC can be used as a probe for the gluon TMDs in the proton, which for the moment are very poorly known experimentally. And so this is the process that we're looking at. It's semi-inclusive DIS, and the usual CIDIS is one of the hallmarks of the TMD process. So at first sight, quite naive idea that we have is let's try to extend it and just consider an outgoing heavy quarkonium instead of a light meson pair, as is usually the case. So of course, first things first, if we want to try to describe a process like this, we need to have a hard scale, which in this case is delivered by the virtuality of the exchanged photon and by the mass of the heavy Charmonium. And we will assume that these two values lie in the same ballpark. So in reality, the hard scale will of course be a combination of both. And now a second scale that arises in this process is the transverse momentum of this outgoing quarkonium. And we will specifically look at the kinematics in which this transverse momentum is small with respect to the hard scale. And this is the typical TMD kinematics. So in usual CIDIS, in which we consider an outgoing pion, for example, you can prove that at all orders in perturbation theory, TMD factorization holds, which means that the cross-section can be written at all orders in perturbation theory and at leading twist. You can write the cross-section as a convolution of a lepton tensor, this part is trivial, of a hard part, and of a hadron tensor, which describes the parton content of the proton. And so we will assume somewhat naively that this works as well in our CIDIS with a quarkonium. And so there will be some caveats that I will sketch in the second part of this talk. So let us start here with the hadron tensor, which describes the gluon content of the proton. This was analyzed already 20 years ago, more or less, Mulders and Rodriguez. And as you can see, the proton at the gluon proton content of the proton can be parameterized in function of different gluon TMDs, so which describe the three-dimensional gluon content of the proton in momentum space, as well as the spin correlations. And even if we consider just an unpolarized proton, already two different TMDs play a role. Of course, we have the unpolarized gluon TMD, the standard one, but also linearly polarized gluon TMDs can play a role even in an unpolarized beam process. In the case where the proton is transversely polarized, of course, the phenomenology becomes a lot richer, because now we will be sensitive to the gluon-Sivers function, to circularly polarized gluons, and to two different kinds of linearly polarized gluon TMDs. So now let us consider the second part of our factorization formula. This is the hard part. So as long as the hard scale is high enough, we can try to describe the scattering, the partonic scattering, in terms of perturbation theory. But of course, here in this case, we're also concerned with the bounding mechanism of the heavy quark pair into the quarkonium state. And so one of the most advanced ways to try to handle this is invoking NRQCD, which is an effective theory to handle these extra degrees of freedom that come with the massive states. And so one of the features of NRQCD is the fact that it features a second expansion parameter. And so next to the coupling constant, we also have to consider V, which is the momentum of the heavy quark pair, the relative momentum, sorry, velocity, the relative velocity, excuse me, of the quark pair in the rest frame of this quarkonium state. And at leading order, at zeroth order in this parameter, the bound state is in fact directly the correct bound state of the quarkonium. So the quark and antiquark are directly bounded with the correct quantum numbers of the shape psi. Of course, part of this computation is non-perturbative, right? Because we're concerned with the hard scattering mechanism and with the hadronization mechanism of the pair into the bound state, which means that we will be sensitive to some non-perturbative information. And in this case, or the way this is encoded in NRQCD, is into the so-called LDMEs, or long distance matrix elements. And these need to be in the color singlet case, like this one. You can try to get them from potential models or from lattice calculations. And other ones you need to try to extract from data. So this is the so-called color singlet mechanism, because the bound state is directly the state with the correct, so to say, quantum numbers. If you now go to higher orders in NRQCD, if you consider higher expansions in the relative velocity, you encounter the possibility in which the quarkonium, in which the heavy quark pair is bounded in some kind of higher excited state, which carries QCD color and only hadronizes later. And in particular, we could consider the 1s0 and the 3pj, with j going from 0 to 2 state, which, as I said, correspond to higher orders in the NRQCD expansion. And as we would guess parametrically, and this is also reflected in the available extractions, the LDMEs, so again, these parameterize the non-perturbative information on this bounding mechanism. The LDME for the color singlet mechanism is of the order of 10 to 100 times larger than the one from the color octet mechanism. However, as you can see, if we consider DIS, it's impossible to form a colored state. To form a color singlet state from an incoming photon and incoming gluon. So this color singlet mechanism will always be accompanied by the emission of some kind of soft gluon, and it will be perturbatively suppressed. It will be higher orders, at least in QCD. And so now the question is, for our process, which of the two mechanisms will be dominant? And it turns out that if you consider large C parameters, so Z is the inelasticity of a variable, and if you consider high enough Q squared for dualities, it turns out that somewhat counterintuitively, the color octant mechanism is the dominant one. So as long as we place a strong enough cut on Z, we can strongly suppress the color singlet one. And for the picture here, I used one set of LDMEs, but this holds a similar suppression holds for all the different sets of LDMEs that we could find in the literature. So we will assume from now on that at least at the current order of our analysis, we can consider simply the color octet mechanism. So with this being said, all the mechanisms, all the ingredients, are in place to present the cross-section. We simply have to sketch maybe fast this reference frame in which we will present the cross-section. This is what is almost always used if you do spin physics at colliders. So we will consider the so-called lepton frame, in which the proton and the incoming photon lie on the same axis. And if you then experimentally also measure the outgoing lepton, you can consider this so-called lepton plane, as you can see, and define the two angles that become important in what follows. So phi h here is the angle of the outgoing quarkonium, the azimuthal angle of the outgoing quarkonium state with reference to this plane, and phi s is the angle of the spin of the proton. And so this is the cross-section. I slightly switched notations. So this phi t here is the phi h of the previous picture. And as you can see, so this is our cross-section for an unpolarized proton beam and for a transversely polarized proton beam. And what is interesting here is that every contribution couples to a different gluon TMD, of course. And all these gluon TMDs come with a different azimuthal modulation. As you can see, and as is expected, the unpolarized gluon TMD doesn't have any modulation whatsoever. The linearly polarized one has a cos2 phi modulation, which is very typical for this kind of processes. And if we consider then a transversely polarized proton, we will get more elaborate combinations of angles, in which, of course, the spin of the proton also plays a role. And so these modulations, this is a bit the first conclusion. So these ratios could be used at least in principle to try to extract these gluon TMDs, this very poorly known gluon TMDs. Because for each modulation, you can probe the ratio of the moment of this ratio over the unpolarized one. And as a result, hard factors and a lot of prefactors will disappear. And that means that every one of these ratios becomes equal to the ratio of one of the polarized gluon TMDs and the unpolarized one. And here I present some of them as a function of y. Of course, gluon TMDs so the do is probe the maximum value of this asymmetry, since each and every one of the polarized gluon TMDs is always bounded by the unpolarized one, I can simply put them equal to the unpolarized one to show the maximum value of the asymmetry that you could possibly get. And this gives us an idea of the sensitivity of our process in the kinematics that we are considering to this certain polarized gluon TMD.
You have
And
2 minutes left.
2 minutes left.
Yes.
Very bad. Okay, I will do my best. As you can see, predictivity is completely lost. This is the quite dramatic message of this picture here. So for 2 different sets of LDMEs, results are vastly different. And this is maybe the main message of the talk that I want to give, that what we tried to do here was mixing collinear physics with there is someone with, thank you. So the problem is that these LDME sets that we use to parameterize the hadronic part of the bounding mechanism, they're all extracted at large KT. And this is a huge problem because for TMD factorization to hold, in cities, for example, we always have to consider also the transverse momentum dependence of the outgoing hadron state. So if you consider cities at low KT, you have to consider as well, instead of the usual fragmentation function, you have to consider the TMD fragmentation function. And the same in some sense you have to do for the LDMEs. You have to take the smearing or the TMD dependence of these quantities into account. And so I will just sketch maybe in 1 minute what the idea is. So I think the upshot will be that we have to measure them. But a part of this, part of the transverse momentum dependence of these LDMEs, we can in fact calculate. The perturbative part of this we can calculate. And this we can do by comparing collinear factorization to TMD factorization for this process. So in the collinear regime, the PT of the outgoing quarkonium is generated by the recoil of some part that we didn't measure. This recoil in the low PT limit of this process can be absorbed in a D-clap ladder. If you then consider the TMD regime, this is the one that I presented in the first part of this talk, you can also consider the high PT limit of this process. And the high PT limit of this process, of course, PT is not intrinsic anymore. This cannot be because it's larger than the hadronic scale. And it stems from soft or collinear radiation in the evolution here. And the high KT limit of this TMD evolution is exactly the D-clap ladder that we had here in the low PT limit of the collinear calculation. And so matching these 2 calculations, it turns out that large logarithms appear in the hard scale and the transverse momentum. And these can be absorbed in a new definition of these LDMEs, which we might call smearing functions, or our friends from SCET call them shape functions. So again, I think these need to be measured at low PT, but as I showed here, there is quite a specific and rather simple way to at least calculate the perturbative part of them. And so then the last part I will skip, and I will do the same for my conclusions. Thanks a lot for your attention.
Thank you very much for this nice talk. We have time for some quick questions. I think Zurek has a question.
I mean, you have shown that there are 3 terms, essentially, which you don't know, but do I understand correctly? In principle, each of them can have completely, in principle, can have completely different KT dependence. So my question is any chance to disentangle this, or you are going to assume that KT dependence is the same? I understand that you are saying that AEC will be able to help us to disentangle these contributions.
Well, so, but which contributions do you mean? Do you mean from the
I mean, there's
LDME?
different gluon distributions.
Sorry,
different gluon distributions.
Different gluon TMDs.
F1, H, perp, and so
on. Yeah, then we will have to compare to other processes, of course. Huh? So we will need to extract the unpolarized gluon TMD from a different process to try to get the polarized counterparts from this one.
No, but so far nobody did it, right?
No.
So you're
well,
waiting.
yeah, there are some attempts already, but yeah, data is very scarce at the moment. It's not
so
so
you are
easy to do
waiting for new data.
Yeah.
Okay.
Yeah.
Okay.
There is some universality, but okay, I went very fast. But in the LDME part, so you could say that these are the counterparts of the fragmentation functions. We see that for different bound states, different excited states of the bound quark pair, this KT dependence turns out to be the same. So at least there seems to be some kind of universality.
Okay, thank you.
Welcome.
Thank you very much, Peter. And now we move to our next speaker, who is Ashish Thampi on behalf of Belle 2 collaboration. We'll talk about Charmonium and bottomonium at Belle 2.
Yeah, hi, can you hear me?
Yes, we can hear you.
Okay. I think
we can see your slides, yes.
Is it full screen? I think, right?
Yes.
Yeah. Hi, I'm Ashish Thampi on behalf of the Belle 2 collaboration. Today I'm going to talk about the Charmonium and bottomonium spectroscopy at Belle 2. We know quarks bind each other to form hadrons, mesons, baryons, pentaquarks, etc. The conventional hadrons according to the Gell-Mann-Zweig constituent quark model. Later, QCD motivated models predicted the existence of hadrons with more complex structures than simple QQ bar mesons or QQQ baryons, like a tetraquark, which can exist as diquark, diantiquark, or a D0 molecule. Quarkonia are the QQ bar states with the same flavor quarks. Here we talk about Charmonium and bottomonium. Theories predicted a number of states in this spectrum. Before the discovery of X3872, the states in these two spectrum, which were established from the experiments, were in a good agreement with the states predicted by the theory. Then after 2003, like we have a lot of B factories in the world, and
Ashish, a lot of people cannot hear your sound. So could you
Yes,
just
we can
check?
hear you, Ashish.
Hi, hello.
Now we can hear you again, yes.
Okay, so where was I lost?
The last slide.
Okay,
Yeah,
here.
middle of slide 4, I think. Yeah, or yeah.
Okay, so okay, so okay, I will explain. Like Belle 2 dictator is an upgrade from the former Belle dictator. So with the installation of pixel dictator, we improved our vector resolution to 25 micrometer, and now we have a time of propagation dictator with a time resolution of 50 picosecond. And the two inner layers of the Kelong muon dictators of the and the old layers in the end cap is replaced by the scintillators because of the large background. And the readout electronics are replaced in the electromagnetic calorimetry.
We have lost you again, Ashish. We still cannot hear you.
Problem.
Now, maybe?
Like you're not even a feeble voice, like it's
Now
mute
we
or
can
what?
hear you, but suddenly it mutes. Yes.
Okay, okay. Hmm. Okay, so the good thing about the Belle 2 is we have a 30 times higher luminosity than Belle, and thanks to the higher beam current and the improved beta function at the interaction point in Belle 2. Now I will talk about the potential of Belle 2 in the Charmonium and the bottomonium spectroscopy. We know X3872 is the poster boy for the Charmonium states. The recent study from LHCb, from that study we have the best bright Wigner width is 0.96 MeV. The upper limit for this X3872 from the Belle data is 1.2 MeV, which is estimated from the JPSI pipe IDK. A recent study using the Belle 2 simulation, we are using the X3872 D0 D0 Pi 0 DK. We expect a greater improvement in the width as we get higher luminosity in the future. Why we use D0 D0 Pi 0 in Belle 2 than we did former in for JPSI Pi in Belle is because of the lesser Q value for D0 D0 Pi 0 for X3872. Lesser the Q values, we have better precision of width. So this is what we expect from the 50 autobahn inverse data from Belle 2 for the X3872, Y4230 and Z4430 states from these productions. We are expecting this high signal yield for these states, and with this high yield on these states, the amplitude analysis will be possible, which was not in Belle. We have a better slow pion detection at Belle 2 compared to Belle. Our slow pion reconstruction efficiency is measured to be greater than 60%. So this enables for the search for exotic at DD star threshold. Talking about the Charmonium in the initial state radiation process, Belle 2 can provide inputs in the discussion for the line shape of Y4230, and we can search for the strange partner of Z3900 in the JPSI KKDK. Also, the study on the cross sections of exclusive CC bar plus hadrons is also possible. For looking at these XYZ states, these are the golden channels we are looking for in Belle 2. We are expecting a very lower statistical error when we attain a 50 autobahn inverse integrated luminosity. This initial state radiation process is a unique case at E plus E minus machines compared to other B factories like LCB. For bottomonium spectrum, we know ZB states were only found so far in epsilon 5s decays. Super GeKB can reach a center of mass energy of 11 GeV. So this epsilon 6s run will be possible in the future. With the high luminosity, for the first time, the study of radiative transition between bottomonium states will be possible. And we are looking for the conventional states search in the epsilon 6s and epsilon 5s production. We use both single transition and double cascade and fill the remaining spectrum to measure the effect of coupled channel contribution. And we can search for the missing pi pi or eta transitions in the epsilon 3s exotic transition to constrain the further theoretical models. For the Charmonia of in epsilon 3s production, these are the Belle 2 goals with the 300 femtobarn inverse. We have a 5 times more sensitivity in the inclusive production from epsilon 3s compared to Belle, and we are expecting a 15 times in double Charmonium. Now I will just give an update about the progress we did in Belle 2 using the early stage data we accumulated in this Charmonium and bottomonium spectrum. X3872, we reconstructed the B plus minus and B 0 from pi pi j psi k. We used the 62.8 femtobarn inverse data from Belle 2, and we used the standard selection criteria we use in Belle 2 for the particle identification, and we removed the continuum using the cuts in number of tracks and the Fox-Wolfram moments. The kinematic variables used are, you can see here, like the pi plus pi minus invariant mass, the beam constraint mass, and the energy difference. So we got the first evidence of this first measurement of this X3872 at Belle 2 with 14.4 events compared to the 170 events in the 772 million BB pairs in Belle. This is actually a very good number in Belle 2. For the Charmonium in the initial state radiation process, we were able to reconstruct the pi plus pi minus j psi in the ISA process. We used the normal PID requirements, and we used a cut for the j psi invariant mass, and the initial state radiation photon was not required because of we had a high efficiency, and we applied a cut for the missing mass square for j psi pi pi. We got a clear evidence of psi 2 as signals, and this is for the j psi 2 mu mu and j psi 2 e plus and e minus using the 37.8 femtobarn inverse data. So our next step is for the Y4230 rediscovery. We are expecting a 60 total events with the 100 femtobarn inverse integrated luminosity. In the bottomonium, for the initial state radiation process, for epsilon 2s to epsilon 1s and epsilon 3s to epsilon 1s or 2s. And we will also look for the direct transition of epsilon 4s to epsilon 1s and 2s. All these signals are we got observed in the early Belle 2 data. We can see the peaks with the 2s to 1s, 3s to 1s, and 4s to 1s states using the 72 femtobarn inverse data. This is some detailed plot of that. This is a Dallas plot for the same study. These clusters represent the signal transitions for these epsilon states. The future studies in these decay modes are like we are looking for this invariant mass in the pi plus pi minus in this epsilon 4s transition. Okay, so this is how I summarize the talk now. Like our main focus is to collect epsilon 4s on peak data. Now we are at the 100 femtobarn inverse stage. by end of 2021, we are expecting to reach the 400 Femtometer based luminosity, which is corresponds to the Babar data. By the middle of 2022, we hope we will cross the Belle luminosity, and after that we go for an N-month upgrade, and then we continue our studies. The near-term non-epsilon forest proposals are like to study the YB 10753 on peak. We are looking at the center of mass energy of 10.751, and for the additional points of the BB bar decomposition, we are scanning for these energy center of mass energy. After the upgrade in 2022, we are planning for a 11 GeV center of mass collision for the epsilon 6s on peak data. And Quarkonium and this XYZ is one of the main components of the physics program in Belle 2. From the early data in Belle 2, we were able to rediscover the 1 minus CC bar and BB bar states and X1372. Our statistics will be soon comparable to Babar and Belle. Thank you for giving me this opportunity to give the updates on behalf of the Belle 2 collaboration. We are spread across the 26 countries and 120 institutes with members more than 1,000. Yeah, that's all from my side for today.
Okay, thank you very much, Ashish. Very nice update on the performance on Belle 2.
Yeah.
Are there any questions from Ashish? Okay, so no one is raising the hands. I have a small question. You're talking a lot about Quarkonium. Anything about the V sub C? Is this something that Belle 2 is keeping in mind? Is taking what are the prospects? You know?
Okay, from the updates I got, I didn't. I don't know about this study is ongoing. Maybe
it's a completely different group that does the V sub C. It's not considered like Charmonium or bottomonium. Sorry. Okay, thank you very much one more time, Ashish.
Okay, thanks.
Now we move on to the last speaker of this session, who is Miguel Ángel Escobedo from the Galician Institute for High Energy Physics, and we'll talk about the dipole picture and the non-relativistic expansion.
Okay, thank you very much for. Can you see my slides?
Yes, we can.
Okay. Well, I want to thank the organizers for the opportunity to present my work here. So this is work in collaboration with Thomas Lappi and has been published in this paper. So, okay. So first I will go to the introduction, then I will discuss Quarkonium light cone wave function in the non-relativistic limit. And then I will discuss some cross-checks, and then I will discuss exclusive Quarkonium production in the high virtuality limit. So, well, the motivation is to study exclusive Quarkonium production, which is interesting and can be studied at low X in DIS and in UPCs. And it's interesting because it's as exclusive process, it depends quadratically on the gluon density. And on the other hand, we expect Quarkonium to be less sensitive to non-perturbative physics. So we do the computation using the dipole picture, in which at the leading order, the cross-section will look like this, which has different elements. The first one is the virtual photon wave function that has a transverse extents of the order of the inverse of the virtuality, and therefore is dominated by perturbative physics. Then we have the dipole cross-section, which encodes the information about the gluon content and saturation that we want to learn about. And then we have the wave function of Quarkonium. So that next to in order, structure is a little bit more complicated because you can consider contributions of the focus state in which you have a Q bar gluon and so on. So our aim is to learn about the nucleus, but in order to do that, we need an accurate description of the wave function of Quarkonium. So this has been done in several ways in the literature. Here I'm going to focus on using the non-relativistic assumption that has been widely used in the literature in other contexts. It's a well-defined limit of QCD, and therefore it is theoretically interesting. And at leading order, it has already been used in the dipole model. Okay, so, well, this is interesting because it can lead to several simplifications. So on one hand, we have the scale of the heavy quark, which is definitively bigger than lambda QCD, and therefore is perturbative physics. Then Quarkonium is a non-relativistic system in which the velocity of the heavy quarks around the center of mass is small, and this means that the spatial part of the momentum goes like mv, and by the virial theorem, the binding energy will go like mv squared. This implies that there is a part of the physics that at the scale m, which is always perturbative, and then it is interesting to separate from the rest of the computation. And on the other hand, from these other lower energy scales, whatever happens at the scale m will look like a local process. Okay, so first, now I go to the computation of the wave function. So we are using the non-relativistic limit. What we mean by that is that we consider that the wave function, the leading contribution comes from the non-relativistic degrees of freedom. We allow relativistic degrees of freedom, but they will appear as a perturbation, which in the light cone means that they appear for a small time. And here by non-relativistic, we mean quarks that have a transfer momentum much smaller than the mass and a momentum fraction close to 1/2. So at leading order, we have this Vitesse-Salpeter equation, and since we only take into account a non-relativistic degrees of freedom, it is equivalent to a Schrödinger equation. Now we start to compute corrections, and we look into the component of the focus state in which we have a heavy quark, a non-relativistic quark, and a non-relativistic antiquark. But we look from the contribution or the correction coming from relativistic particles using this color code in which relativistic particles are red and non-relativistic particles are blue. So we have this kind of contributions that are actually the wave function renormalization of the non-relativistic quark. And we have also this other type of contributions that we are not going to appear explicitly in our equations because we can always reabsorb them by a redefinition of the potential, and then their effect will be to indirectly modify the value of the non-relativistic wave function at the origin. Now we move to the component of the focus state in which we have a relativistic quark and a relativistic antiquark. So in our framework, this is equivalent to this equation. So what this means is that we have something proportional to alpha s at the scale m multiplied by the non-relativistic wave function. And because this is a hard scale, from the point of view of the blue part, this is a local process. So this means that this is proportional to the non-relativistic wave function at the origin. And we also have the focus state in which we have a relativistic quark, a hard gluon, and a non-relativistic antiquark, which is also proportional to the non-relativistic wave function. So what we have actually is this mathematical structure in which we have the 4 light cone wave function of Quarkonium, and if we integrate out over multiplied by a test function in the longitudinal momentum zeta, then we always can expand it in this way, in which we have here the derivative of the non-relativistic wave function at the origin and some hard coefficients that we have to compute. Okay, just let me know that this expansion in K is actually an expansion in the velocity, and the velocity will go like alpha s at the scale mv, while in these hard coefficients, the expansion parameter is alpha s at the scale m. Okay. So if we want to compute the cross-section, we will have a formula like this. So regarding the correction with K from K different from 0, that we can call them relativistic corrections, they first enter at next to leading order in alpha s, and they have been recently computed. And regarding the corrections in the hard coefficients, the first one enters at next to leading order, and it is what I'm going to discuss in this talk. And just let me mention that, well, this is next to leading order, but with a smaller alpha s, because it's an alpha s at the scale m, while the relativistic correction is next to leading order but with an alpha s at a different scale, which is bigger. So this means that depending on the details of the computation, one can dominate or the other. Okay. So with this, I show here the result for the QQ bar component in the longitudinal polarization and in the transverse polarization, and also for the QQ bar gluon component. Okay. Now let me show some cross checks. So one cross check that we can do is to study the light cone distribution amplitude, which in the light cone gauge correspond to what we have computed in the limit r equal to 0, and to check that it fulfills ERBL evolution. So this is not entirely trivial, because we have to regulate divergence that appears when we do this limit, which we do using dimensional regularization, and we get this for the longitudinal polarization and this for the transverse polarization. And if we do the derivative, in fact, we see that the ERBL equation is fulfilled for our computation, which is good. And another cross-check that we did is to compute the quarkonium decay into leptons. This was already computed in non-relativistic QCD, and this was the result they obtained. So in our case, we were using they were using dimensional regularization, while we are not using dimensional regularization exactly, because we are using a cutoff to regulate the longitudinal components. So this is the diagrams that we need to consider for that with our color code. And this is the result that we got. And as I said, we got something different because our regularization is different. We have a cutoff here, but we have checked that the origin of this diversion is the Coulomb singularity. And in fact, what we need is that the non-relativistic wave function at the origin fulfills this equation. And if we went back to the Peter-Salpeter equation, and we check that indeed this equation is fulfilled. Okay, so with this, we have all the ingredients to study the exclusive quarkonium production in the high virtuality limit. So the general case was very recently studied, and you can see more on Yanni's talk on Thursday. So here in our paper, which is previous to this other one, we only studied the high virtuality limit because we needed to study the general case, the photon wave function at next to leading order with massive quarks, which also appear recently. So what I'm going to discuss here is how in this regime we can check that all the divergences cancel. And on Thursday you will see more details about the phenomenological applications, and we get an evolution that is consistent with the Jim-Bock evolution. Okay, So first at tree level, here you have a hidden dependence in X0 because the target fulfills Jim-Bock evolution, and the non-relativistic wave function must evolve with X0, as was explained when we discussed the Quarkonium decay into leptons. Then we have the corrections from the one loop photon wave function. We were computed by Guillaume, and we use his results. And regarding Quarkonium wave function, we have here the dependence with mu, which is equal to that of the photon, and the dependence with X0, which has a piece that is similar to that of the photon, and another piece that cancels the Coulomb singularity in the non-relativistic wave function at the origin. And regarding the QQ bar gluon focus state, there is a piece that cancels, well, no, sorry, the evolution with mu cancels the rest of the variances of the photon and Quarkonium wave function. And regarding X0, there is a piece that cancels the Jim-Bock evolution, and then another piece that cancels the evolution of the photon wave function of Quarkonium, except for the piece that has to do with the Coulomb singularity. And with this, I go to the conclusions. So we have computed the next two linear corrections to Quarkonium wave function in the non-relativistic limit, and we have checked that it fulfills the ERBL equation that the light cone distribution amplitude must fulfill, and we recover results for the Quarkonium decay into leptons. And to our knowledge, this is the first computation of this in the light cone gauge. And we have checked that when this result is applied to exclusive Quarkonium production, all divergences cancel. So we are ready for phenomenological applications, and you can see more on the talk of Yanis on Thursday. That's all. Thank you very much.
Okay, thank you very much, Miguel Ángel. So questions for Miguel? You can raise your hand. So if there's no one, I had a question. A small question regarding why I didn't understand very well. Why cannot you use dimensional regularization?
Well, it's not that we can use it, but I think it is usual in the dipole picture to regulate X0, so the longitudinal component with a cutoff. I mean, this is how the Jim-Bock evolution is normally written up. Mm-hmm. So I think it's actually, I guess one could also write, I suppose it's written where the Jim-Bock evolution with dimensional regularization, that is not the usual practice.
Okay, okay. I was just curious. Thank you. So thank you very much.
Thank you.
So this is the end of this session. So thank you very much once again to all the speakers for the very nice talks.
I wanted to ask you if I could check sharing my file for the next session.
Yes, of course.
Yes, please. Just give me 1 second. Yeah, everyone, I'm going to stop recording now because the session's over. 15 minutes from now, I will put up a timer on the screen so that everyone will know when we start the next session. So yeah, have a good lunch. Thank you.
Okay. Thank you.
Can I share now?